So I drew Steven going at 20 meters per second on this frictionless surface. He'll reach a frictionless hill. As soon as he starts going up the hill, he's going to lose speed. He's going to lose kinetic energy because some of it's going to be transformed into gravitational potential energy. And the question is he going to make it to the top of the hill? And essentially that means, does he have enough kinetic energy right now to match up with the amount of gravitational potential energy he would need at the top of the hill? I'm going to set my reference height to where Steven is now. This is going to be my reference level. And what I'll do is I'm going to calculate how much kinetic energy he has now. Which would be k equals half mv squared. Which I believe this works out to be 12,000 joules, or 12 kilojoules. All right, and I'm going to try to compare this with gravitational potential energy. At the peak of the hill, which would be mgh. So work that out, 69.8 and times 10 meters. $5,880. So it looks like he has plenty of energy. There's not going to be any risk here. He's got an excess of more than 6,000 joules actually. So he's actually still going to have speed when he's at the top of the hill. How much speed? Well, he's at 20 meters per second now. So at the top of the hill, how much joules does he lose? He loses almost half of his joules. Not quite half. But he loses about half of his kinetic energy joules. It transforms into gravitational. So if he's got half as much kinetic energy, what's his new speed? Well, it's not going to be half the speed because the speed in the kinetic energy formula is squared. I think it's actually going to be a factor of 1/√2 of the original speed. Did not really ask for that there, but I'm going to add that in. What will his speed... I'll use a different color. So the answer is yes, and here's a follow-up question. What will his speed be at the peak? So at the peak, what I can do is figure out the kinetic energy, so K at the peak. And that's going to equal the original kinetic energy of 12,000 joules, subtracted by how much of that got transformed into gravitational potential. So this will be 6,120 joules. Left for kinetic. And when I substitute that into K equals half mv squared and isolate this for the speed, that would be 2 times K divided by m and then square rooted. Okay, let's see what that turns out to be. I'm going for, something in the mid-teens. Okay, so we got 14 meters per second. So another question we could ask, a follow-up question, is when he gets to the peak of the hill, is he going to stay on the hill or is he going to fly off of it? And that's actually a question we cannot answer because we did not exactly get to that stage of the unit. Ran out of time there. That would have to deal with what I would call non-uniform circular motion. So there's actually a speed. There's actually a speed that if you're going faster than that speed at the top of a hill, you might actually find yourself airborne. You will not stay on the hill. But maybe that'll be something you learn about in your next physics class.